chat window up so I can see what's up. Yeah, so we'll do the last little bit on equilibria here. So equilibrium constants sort of keep popping up. They pop up again in the next chapter. And they'll pop up again in your other courses like biochemistry and stuff. But this will be the last time that we kind of really focus on them in any kind of specific sense, where they're not just kind of ancillary parts of the course. Compared to acid-base stuff, this isn't bad. So, yeah, what you want to know, let's see, what do you want to know? So we're going to deal with solubility here. Get my... So we're talking about solubility here. And we're going to talk about the thermodynamics of solubility. And then after we talk about thermodynamics, we're going to move into what's called kinetics. And we'll talk about what the differences are between thermodynamics and kinetics. So if you go on the GChem website, you know, there's this sort of review of ionic equations and solubility. Let me see if I can pull up some solubility rules. Yeah, well, so there's a solubility table. So I'm used to teaching this where you don't have, you know, access to the internet while you're taking the exam. But so this is your solubility table. So if you're trying to figure out when you combine two things, like so when you take two, let's see, let me think of an example that's not on the GChem website. Silver chloride one's a good one. Let's say, yeah, calcium carbonate is a good one. Okay, so if I take two salts, let's say like calcium chloride, and I mix it with another salt, sodium carbonate. And so these are aqueous, so I've dissolved these up. These can undergo a reaction where the cation of one of the salts will sort of react with the anion of the other salt, and you'll form an insoluble salt. It's like calcium carbonate, and usually the other salt will be soluble. You were correct about that. Thank you. Calcium chloride deserves a subscript. Let's see, there's probably some balancing I need to do here then. Maybe we can't have that, so we'll put a 2 there. That screws this up. Why am I so dense on this? Sodium chloride, sodium. Oh, I see what the problem is. It's because I forgot the 2 here too. Also 2 subscript for carbonate, yeah. Let me go ahead and put in all my charges. So chloride should have a 2. There we go. I think everything's balanced. So yeah, so these two things will come together and form this insoluble salt on the right-hand side. Let's see, I guess now I do have to, I think just a 2 now will fix this. Yeah, okay, now it's balanced. So these things will, the main thing though is that these things will come together and you'll form an insoluble salt. So you'll notice this is a solid, And I've indicated that here with the change in state in parentheses. And so calcium carbonate is one of the more common, or like a more familiar, I guess I should say, compound. That's what if you've ever been into like the green belt, all of those bluffs over there are limestone. Those are all calcium carbonate. And so you know from experience that calcium carbonate is not very soluble, right? If it was soluble, then those wouldn't exist. They would just dissolve when it rained. Chalk is also calcium carbonate, or that stuff that they go in, I think it's calcium carbonate as well. The stuff they use for baseball fields to make the white lines, those are all calcium carbonate. But so if I take it's not like all carbonate salts or all calcium salts are insoluble. If you buy calcium chloride, that's perfectly soluble in water. And if I buy sodium carbonate, that's also perfectly soluble in water. So sort of what you're thinking about here is I have one solution where I've got calcium chloride. So when it's aqueous, right, it's just sort of broken up in solution like this. And I've got another solution of sodium carbonate. And then I'm going to mix those two together. So I pour those into a bigger beaker, let's say. We're not super worried about concentration at this point. And what I'll see is the sodium and chloride is going to stay in solution. So those stay dissolved. But then I'll see at the bottom, I'll start forming this precipitate. So we'll call it, this solid starts to form at the bottom. And these chunks that I see down here are calcium carbonate. You can write out sort of a net ionic equation for this. So when we're talking about like an acid basis, I would talk about how like, if you're looking at something like sodium acetate versus potassium acetate, these are basically the same thing. We don't really care very much about the sodium or the potassium because they're spectator ions. Here, we can look at that sort of explicitly. Hang back after office hours and we can talk in between, Frida. Like in that 5-10 minute break, we can have a little quick talk. Okay, so we've got calcium carbonate. We can write a net ionic equation here where we just leave out all the crap that we don't care about. So we could say, we could just say calcium plus carbonate goes to calcium carbonate. So this ignores all of these other spectator ions. Like I'm leaving out the sodium chloride, I'm leaving out the sodium, and I'm leaving out the chloride. And so this is why sometimes like in the acid-base chemistry chapter, instead of writing out this, I might just write out this, because this just doesn't really matter in the chemistry of the things. And we can kind of see that here if we, sorry, I keep erasing those. I usually don't do that, but it's sort of adjacent to what we're talking about. It's not necessarily part of the lesson. You can kind of see that here. Like, so I could take calcium chloride, for example, up here and replace it with calcium bromide. And I could replace sodium with potassium. And I would still get calcium carbonate out of this. Only now the salt I would be forming would be potassium bromide. And so the net ionic equation for either one of these is the same. So these are spectator ions. Here, I'll outline what they end up. I mean, it depends on how you write it. I think it's fine to call them spectator. But all these ones in pink are spectator ions. They don't really do anything. They start out dissolved and they end up dissolved. And we can see that up here. We have this and we have this. Down here, nothing's really changed. They're still just kind of floating around in solution. So when we talk about solubility equilibria, this is sort of the starting point of just understanding these basic solubility rules. And I think in most, I know some of you guys are coming in right off of high school. I know in General Chemistry 1, actually, do I know that? It's been a while since I've taught the first class. We teach something about solubility. I think we give an overview of the solubility rules. And in most high school classes, if your teacher's doing their job, then they should have taught you about solubility. So this is good practice for writing these subscripts. Like, see how I've got these subscripts and I'm balancing equations and I'm balancing charges. I know some people come in pretty weak on that, and it takes some practice to get. That's going to become really crucial, not in this unit, but in the next unit when we go to electrochemistry. We get back to balancing equations, but we balance redox equations, which are kind of tough. So you don't want to end up like somebody corrected me and said, hey, you need a subscript of 2 here. That's where you want to be in your thinking, where you can actually like catch those mistakes. You don't want to be struggling with that, or you're gonna be kind of falling behind there. All right, so that's a quick review of solubility. The solubility rules that you can kind of access while you're doing an exam is just look at that link I posted in the chat. All right, let's go a little bit deeper now and talk about solubility equilibria. Okay. This is just, I don't know what to call that, solubility, just kind of general rules about it. Yeah, when we want to start characterizing solubility in sort of a deeper way, we can talk about solubility equilibria. So that's when we start pulling out some of these thermodynamic tools we've been developing, like the mass action expression. So let's think about this again. So if you've ever let's see, if you're trying to make a solution of something, this is something you maybe have done at least once, so you're trying to make, let's just say you're taking salt and you're dissolving it in water. If I take some salt, sodium chloride, it starts out as a solid, it's just table salt, and I keep putting it in water, and I stir it, and I stir it, and I stir it, and I stir it, and I stir it. For a long time, it'll just keep dissolving, and I'll just get more and more concentrated sodium chloride in the water. But at some point, I hit this, I hit a point where the sodium chloride will no longer dissolve, and I start to form some sodium chloride solid at the bottom, right? There's not a reaction happening, it's just the sodium chloride I'm putting in. I can't fit any more into the solution. There's only so much sodium chloride that can be dissolved in water, and I hit a point where I've dissolved too much, and now any additional sodium chloride I have put in just kind of sinks to the bottom. Or if you've ever made like tea, it's not a perfect example, but like iced tea or something, it's like you can get some in, and then like after a while it just starts to kind of sink to the bottom. You hit this point where you can no longer get any dissolved. This is when the solution is saturated. Or saturation point, I don't know what we call it. Yeah, saturated solution. This is when the max amount of a salt is dissolved. So a salt here, it doesn't necessarily be after salt. Let's call it well, for us, we're going to call it a salt. So a salt here refers to anything, not sodium chloride necessarily, but it could also refer to calcium carbonate or lead sulfate, any kind of ionic compound. I'll put a little thing over here. Let's see, ionic compound of any kind, not just table salt. So sodium chloride is like pretty soluble. That's not something we're probably going to explore thermodynamically. You know, you can make a pretty concentrated solution of salt. The oceans are pretty goddamn salty. We're going to look at things that are like a lot less soluble. So if we go back, KSP calcium, let me pull one of these thermodynamic constants real quick. If we go back and we look at this calcium carbonate thing, so calcium carbonate is an interesting example. Okay, so now we're doing a thought experiment where instead of forming calcium carbonate from mixing two solutions like we did up here, so up here we took two salts that you could go buy at like a chemical stockroom and mix them together to get out the solid. That was sort of our thought experiment. Now instead, we're starting out with a big chunk of it. So we're starting out with a solid. So, you know, I go out to the green belt and I chisel off a bunch of calcium carbonate. And I've just got these big chunks of limestone. That's what these are. So I've got this calcium carbonate that's a solid. And I'm going to put it into a glass of water. And so now we're going to see that it's not very soluble, but there is a teeny tiny amount that will go in a solution. And so if I take this, let's say, and I put it into water, some of this, that's exactly how I wanted that to work, but some of this is going to come off in a solution. So a tiny amount of calcium in carbonate is going to dissolve. It's not a lot. If it was a lot, again, things like limestone would just dissolve when it rained outside. But it is some amount. And so that's what we're describing with this equilibrium up here. We're saying, okay, if we take a big chunk of calcium carbonate and we dissolve it in water, exactly how much is going to dissolve? And we can define an equilibrium constant for that called KSP. But again, limestone does erode, but it's not like crazy soluble. So that's kind of what we're looking at, is like what that erosion looks like. We can define a KSP for this of 3.3 times 10 to the minus 9th. And this is K, so you know, we have this little subscript on it, KSP, but ultimately what we're looking at is the equilibrium constant in the same sense that we've looked at equilibrium constants all along. What does an equilibrium constant describe? It describes, in a sense, the extent to which the reaction goes to completion. So for K, remember, if K is greater than 1, the reaction is product favored. And for K less than 1, it's reactant favored. And the further you deviate from 1, the more extreme the situation is. So here, what do we have? We have KSP equals 3.3 times 10 to the minus 9. That's 8 zeros. So that's the same as saying it's equal to 0.000000033. So that's what KSP is equal to. So this thing is significantly less than 1, right? It's normally what you'd say, like if we were kind of doing this calculation in a non-precise way, you would just round that down to 0, Like if you've got $0.000000033 in your bank account, you might as well be bankrupt. It doesn't really mean anything. But we can measure these. If you have a finely tuned instrument, we can measure this, the concentrations that actually dissolve. And so we see that it is very, very slightly soluble. So somebody asked, Sahajat said, doesn't limestone erode easily? And the answer is, yeah, it does erode. And the reason is because this reaction happens, but it happens to a very small amount. It happens to a very small amount. And so it takes a very long time for it to erode. So if you go out and you look, you kind of look at the limestone out there, you can see it's been sort of carved by water as rain and stuff has flowed over it. But that's been a process that's been happening, over like probably millions of years or something like that. And the reason is that it takes so long is because it's just not very soluble at all. And so that gets dissolved and probably taken away off into the ocean somewhere. But so we can do some calculations and stuff with this. So one thing to note is, that we can write out our K expression for this. So remember that K, I'm going to drop the SP part just because I find it annoying. K is equal to the products times the reactants. I'm sorry, the products times one another, raised to their coefficients. So the coefficient here is just 1. So these things are just raised to 1. Nothing new there. But we always put these over the reactants. But the thing to note here about our reactants, and this is always true for these, is that the reactant is a solid. So that the reactant doesn't appear in the mass expression, the mass action expression. And that's because it's a solid, and remember, solid and liquids do not appear. We only look at things that have that are either gases or aqueous. So these things over here are aqueous, that's why they appear. If it's a solid, it doesn't enter into the expression for K. So if we look at something else, my solubility chart. Oh, I know a good one. Let's say we're looking at iron phosphate. So iron has 2 forms, iron 2 and iron 3. Iron 2 is much less common because it oxidizes readily in the presence of oxygen. So we're going to use iron 2 here. So we're looking at the +2 ion. Of course, phosphate's always -3. So this is a solid, super insoluble. Hold the solubility. This is the nice thing about these the equilibrium constant. Ferris? Yeah, Ferris. Is that you can just pull them up. They're tabulated. If you need to do calculations, they're easy to find. So, and going from, so now I'm looking at one where like I have, what did I use up top? I'm trying to be kind of consistent. Orange for cation, green for anion. If we look at the cation, when you're trying to write these things out, and hopefully this isn't a big problem for you guys, but I know it is just from having taught this class. Some of you guys struggle with this. The subscript just kind of pops out front in the net ionic equation, or when you're just kind of looking at these solubility things, right? So I just carry that over, and that balances the equation automatically. And then we want to write out our K value for this. Again, the solid's not going to appear in it, but the general rules that we learned for equilibria are still going to hold. So we still want to raise this thing to the cube, because it's got a 3 up here. That's where that comes from. And we want to square that one because of the coefficient. So that's what our KSP looks like for that. The SP just stands for solubility product, but again, it's just K, same thing that we've been dealing with all over and over. Yeah, what's the KSP for this reaction? I just looked it up. It's super, super small. You can imagine you need a very finely tuned instrument to even measure these things because such a small quantity is going in a solution. Times 10 to the 29th. That's a crazy small number, right? I'm not even going to bother writing out all the zeros. That's 28 zeros in front of the 1. So iron or ferrous phosphate or iron 2 phosphate or whatever is really, really, really insoluble. So for those of you that are going on to do chemical engineering or oil and gas, like petroleum engineering, especially if you're working in West Texas, which I worked out there for a little while doing. I was working at a startup. We were developing these water test kits. So it's dealing with a lot of this kind of crap. Iron, like when you pull up oil out of the, I guess a little side thing here before we get into this. Some math. Yeah, when you're doing hydraulic fracturing out in the West Texas, you know, you're drilling way down underground, and you've got these reservoirs of oil. And when you pull the oil up out of the ground, you get oil. So you get this, you know, nasty brown shit that's been underground for a long time. But what also comes up with it, what I don't think most people realize, is also water. So remember, oil forms, this is not testable material. This is just an interesting side fact. So you get some oil, you get your crude oil, but you also get water. Because remember that oil forms from, you know, microbes and stuff that lived a long time ago under immense pressures and stuff like that. And so in addition to like kind of all of the carbon organic stuff getting broken down into oil, you also have the water that's left over from the organism. But the water's been underground for like 1 million years, and it's just got all this shit in it. And some of it is radioactive. I don't know what they do with that. I think they pump it back down hole somewhere in some other part of Texas. It's a nasty operation. But a lot of it actually has a ton of like all this iron and stuff dissolved in it. So you pull this stuff up, and it'll have tons of dissolved iron in it. And that can cause a lot of problems. So if you've got like a pipe here, and you've got all this iron in there, and you know, it's reacting with oxygen, you can start to clog these things. And if you clog it, you know, that can be an extremely expensive thing to fix, like several $1 million. And so they're really concerned with kind of how to stop this kind of stuff from happening in oil and gas. And so they'll put in these things called anti-scaling agents to kind of prevent this from forming iron phosphate.
Oh yeah, regarding the fracking thing, also the wells, they're very unproductive. So after like 12 months of pulling oil, they're producing like 10%, and they just run out real quick. So they have to keep finding new wells. So it's very unsustainable. Like,
oh, just like as commentary on hydraulic fracturing in general.
Yeah.
Yeah, I guess that's true. They'll lose. Yeah. I'll take your word for that. I've been out to West Texas before and flown in, and there's just like pump jacks and stuff everywhere. It's a pretty wild operation. I didn't work on that side of things. I was just there to test their water. I don't know that it's any worse than any other oil and gas operation, but anyway, this is not obviously it's not a class on hydraulic fracturing and stuff, but yeah, this is a place where that kind of comes up, solubility equilibria. But yeah, so let's see. So back to the question, does an insoluble compound have an KSP? That is a good question. So all compounds have a KSP. So iron phosphate, for all practical purposes, is insoluble. Its KSP is 1.0 times 10 to the minus 29th. But if you put some in solution, a very, 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 very small quantity of it will dissolve. And so, yeah, what we're kind of measuring, what KSP is a measure of, really, generally is like you're almost always measuring it for insoluble compounds. So we're using the term insoluble. It's kind of a misnomer, right? Or let's say it's an approximation. It's an approximation. Uh, Nothing is truly insoluble. Um, Always some tiny amount of it. There's some probability that some amount of something will be dissolved. At some point, it becomes kind of impractical to worry about. Like if I'm taking like iron phosphate and throwing in a cup of water, for most things, it's not going to be remotely relevant as to whether or not. I got a good example of that. Yeah, so in most cases, you might as well call it insoluble. I'm trying to remember there's a salt you can use. Like if you go to the doctor, insoluble salt for imaging. It was all a lie. Most things you learn are a lie until you get to like graduate school where they're like, look, we never knew what we were talking about the whole time. Here's as much as we know. And you're like, damn. I feel like I don't know, physics is pretty, well, even in physics, everything's kind of half truth, right? Like you start out learning about Newton's law, and then like later on, they're like, actually, this isn't real. It's general relativity. And then at some point, they're like, even general relativity has its problems. Now we got to look at like quantum field theory. Um, there's a lot we don't know about the world. I had a good one, but I can't remember what the hell it is. But if you go in, so is math because you hit calculus and then more after. Yeah. Um, my experience with math, I got a math minor in undergrad. I was double majoring in math, but I like I was in New Orleans when Hurricane Katrina came, and it like totally screwed up my last 2 semesters of college, and I didn't get my second degree in math, and I didn't get an honors degree in chemistry, which obviously I don't really at this point in my career I don't care about. But one thing I realized about math is like you go through all this stuff like algebra, trigonometry, and calculus, and like I was pretty good at that stuff. But then you get to the proofs, and that is like a totally different nightmare. I took a class called abstract algebra, and I was like, I don't know what the hell is going on. This is terrible. I never really, and I kind of got it towards the end of the class, but I skipped out on doing advanced calculus. I would have had to stay an extra semester to do it anyway. Uh, anyway, math gets really messy. Like what real mathematicians do is like really insane. All right. So anyway, so insoluble things uh, are not truly insoluble. Some of it is always going to be slightly soluble. So what we can do, yeah, proofs are rough, man. I don't know if it's because I just never. Yeah, I'm glad you guys have to. I don't know if it's because I never did that. Like I never learned anything about that. Duo push. Yeah, duo push is the worst. I'm glad we all agree on that. Um, but yeah, proofs I like I never learned about that in high school at all. High school it was like here's a formula, plug in some numbers, and then even in college it was like pretty soft. I think I did one in linear algebra, and then all of a sudden in abstract algebra that's the entire thing, and they're like petition to get rid of duo. In college in abstract algebra they were like, all right, now we need to prove things like like 0 + 1 or 0 + a equals a, and I was like, I don't how do I prove that? Just seems like on its like just true of its own merit. So. Um, all right. So solubility equilibria, we can use this to do some solving. OKSP. I don't like that problem. This value, step one for this is that we must. Yeah, so we can use KSP to solve problems where it's like, let's say, if you take a certain amount, of something and you put it in a solution, like a certain amount of iron phosphate or something, and you want to know exactly how much of it dissolved, we can solve that in the same way that we solved our acid-base problems. That is how I at least think of, that's what I think of these things as being useful for. Here's one. Yeah, so the way the problems are typically solved for this would be something like, oops. So we've got copper iodate here, copper 2. So they give you a KSP. Oh, I left out the actual KSP value here. So they say the KSP value for copper iodate is 1.4 times 10 to the minus 7th at 25 degrees Celsius, and they're asking to calculate its solubility. When they're talking about solubility, the way we express solubility is like amount per it's usually expressed in moles per liter. That would be the molar solubility. And then sometimes it'll be expressed more often, honestly, it's at least in practice, it's expressed as like grams per liter or milligrams per milliliter or something like that. But it's the amount that's soluble per some unit volume. That's really what it comes down to. So on the top, in the numerator, you're going to have the amount, and in the denominator, you're going to have the volume. And it's just telling you exactly how much you can get dissolved in some unit volume. So if we're trying to calculate this, we can do it in the exact same way that we've done all of our other sort of problems. Since we know the KSP, how do we want to do this? So you assume that you're at, you're past saturation for these types of things. And you can just set up a Rice table for this. So let's see. So you would start out with like some amount of this over here. So remember, this is a solid, so we don't actually have to care about how much is there. You just have to assume that you have enough that you've gone past the point of saturation, which for most of these things, because the K value is so small, is not very much. So you put a chunk of this in solution, the copper sulfate in solution, and since it doesn't enter into the mass action expression, I know it's kind of confusing, we don't really have to worry about it. We have enough there to where we're going to hit the saturation point. This is our reaction. This is our initial, our change, and at equilibria. So again, we don't really care about this, even though we know that's where it's coming from. We know that however much of this dissolved, 2 times the amount of this is going to dissolve. So at equilibrium, you can see you almost don't need a rice table here. You're going to have X amount of copper and 2X amount of iodate. So this is just a way of saying that if we're trying to figure out the relationship for KSP, we know that it's I'm running out of time here. We'll pick this up when I come back on Wednesday. But if we're looking at this, we end up with this expression here. And since we know KSP because it's given to us in the problem, we can very easily solve for X. Anyway, so we'll pick up, I don't want to keep going past class time. We'll pick up here on Wednesday, but you can see the problem setup is very similar as it is for our other type of equilibria stuff. The only thing that's confusing, like in terms of what you're thinking about, is that you're not starting out, you don't have to worry about with how much of this you have there because it doesn't end up entering into this expression down here. But mathematically and like kind of from a problem solving heuristics perspective, these problems tend to work out to be a little bit easier. So I'll show you how to take this all the way to like, this point next time. But you can solve this and try and think about what X actually represents. And ultimately, we're going to express it in terms of moles per liter. But yeah, we'll probably finish that up. I'll post some modules and stuff for you guys to work on just to kind of keep you on target for the class. And yeah, on Wednesday, we'll probably jump into kinetics after this. That's going to be the bulk of the material for next exam. I don't know if you can see those, but that's all the notes. I'll leave those up for before office hours. Let's see. Oh, the next exam, it's on, go and look at Canvas. It's on there somewhere. I'd have to go and look it up, but it's probably in a couple of weeks, 2 or 3 weeks. November 11th, yeah. When is Halloween? That's not this week, is it?
Yes, it is on Saturday.
No shit. Okay, well, usually it falls in the week. Let's talk about that on Wednesday. What are y'all being for Halloween? My son's being a dinosaur. We actually are practicing trick. The reason I was late to class is because he's been practicing trick or treat. And he'll knock on the door to the office and say trick or treat, and then I'll give him something like a pencil. He's like real stoked about it. He's 2. This is his first Halloween. Yeah, it's super cute. He was like real disappointed that I had to go to work. He's like crying, so I was trying to comfort him a little bit. Anyway, all right, let me take a break here and see if I can get caught up with Frida on the side here.
Okay, greater than 1 is product favored. Okay, less than 1 is reactant favored. This is to Ian.